Okay, so the idea behind a Maxwell-Boltzmann graph is to show the distribution of particles at different kinetic energies within your reaction so that you can illustrate how the changes you are acting upon them would affect your rate of reaction. So the basic way it's laid out is you have a number of particles on the y-axis, energy or kinetic energy across the x-axis, and then you'll have a curve that displays the particle's energy. And it will always start at 0, 0 because you have 0 particles that are 0 energy. It's generally a very steep upwards curve reaching a peak, which would illustrate the average temperature. So this would be where the temperature of the thing, most particles would have the kinetic energy of that temperature, and then it will tail off but never reach the y-axis because there will always be particles with more energy. So it just will cruise along the top, potentially to infinite energy. And quite often we will mark onto your Maxwell-Boltzmann graph the activation energy. So just a little topic 5 reminder that your activation energy is the energy that the reactants required to break all of the bonds. So it's this bit up here that we're looking at. And that would be marked on the x-axis so you can see the activation energy is a particular energy along here, EA. And every particle beyond that activation energy is capable of reacting when it collides because it has enough energy on this graph, enough enthalpy to break all the bonds and for the reaction to start. Particles below this do not have enough energy to do that. So they would be an elastic collision, they'd bounce off one another, you'd get no reaction. So they would be a reaction without the activation energy, so nothing happens, they would stay as their reactants. So let's look at how the different ways that we change the reaction can affect the Maxwell-Boltzmann curve and how that affects the number of particles reacting. So if we change the concentration, what we are actually changing is the number of particles that are available for collision. So the shape of the curve will not change, okay? So the peak will be at the same point because the average energy is going to be the same. It's going to tail off in roughly the same shape, but it will just be lower or higher because there are more or less particles going on. So we can mark on our activation energy, and that shows us that at this point, all of these particles are capable of reacting upon collision. If we halve the concentration, we would halve the number of particles. So, like I said, the shape of the curve would not change, but it would be less high. So the shape would still reach a peak at the same point, but it would just trace roughly through halfway like that. So now, whenever these particles collide at the lower concentration, only these particles in green here are available for reaction. They're the only ones with energy over the activation energy. So as you can see, it's roughly halved it because we halved the concentration, so the rate of reaction would roughly half as well. If we double the concentration, obviously we would go higher, still reaching the same peak. So if we double concentration, it would go up, reach the same peak, and then come down. Ooh, a bit too steep on my drawing there. But now obviously we have more particles at this end, so we would have the pink area available for reaction when it collides. So we would have a higher rate of reaction because there are more particles there. So changing the concentration does not change the distribution of the energy. So the shape will look the same, the peak will be the same, nothing shifts. It would just get higher or lower because there are more or less particles available. So this is very similar for surface area because with surface area, what you are changing by crushing up your particles are the number of particles that are available to collide, so the number that are on the outside rather than the inside of your lump. So the surface area behaves exactly the same way as our concentration one. So if we had our current, let's say, mid-sized lumps, here is our activation energy again. Obviously, it's this section. If we crush up our particles, so we make our lumps smaller, we're now able to access more of the atoms that are inside the original lumps. So it would be like increasing the concentration, so it would go up, reach a peak at the same point, and then tail off in the same way. So we would have more particles over the activation energy, so all of our pink particles would be available for reaction when they collide. And the same way, if we had bigger lumps of the same chemical, there are more particles trapped inside that can't be collided with. So your curve would be the same shape, but lower, and you would have less particles capable of reacting because you have less that are available over the activation energy. So it's just basic statistics in the sense the number of particles available to collide with enough energy is just lower because there are less particles. The amount of energy distribution is the same all the way through. Pressure, again, works pretty similar, but obviously we're not changing the number of particles anymore. We would be changing the volume they are in, so you're increasing the chance of them colliding. So it is impossible to really show this on a Maxwell-Boltzmann graph because one of the assumptions we're making when we draw it is that the volume is going to stay the same, the number of particles are distributed in the same amount of space. So you wouldn't be asked to draw a Maxwell-Boltzmann for pressure. But imagine it's behaving in a similar way. The higher the pressure, the closer the particles are together, the more energy they have, so they're more likely to collide. So you've got more that are over the activation energy. But you will not be asked in the exam to draw one for pressure, but just recognise it would be a similar sort of idea to the concentration of the surface area. Now, temperature is trickier because when we change the temperature of our reaction, our number of particles is fixed. So we're not adding more particles to the system, we're not making more particles available for collision. There's still the same number of particles in there. However, by adding temperature, adding heat energy, you're increasing the kinetic energy, so you are moving things on this x-axis. So because our number of particles is staying the same, when we draw a temperature graph, we have to maintain the area under our curve because we have the same number of particles, so the area under the curve is going to be the same. So when we increase energy, our peak is obviously, our average temperature is going to shift upwards, so our peak is going to shift towards the right of our graph. However, we can't just shift it right and stretch it out more because that would mean there were more particles there. So our peak is not going to be as high. It's going to be a lower peak because we're spreading the particles out over a greater energy. So it's the same number of particles. So the key with increasing the temperature on a Maxwell-Boltzmann is your curve will move to the right and down from the original peak. So if we put our activation energy on, you can see if I increase my temperature, my peak would be further to the right and lower. But I have to try and maintain the area the same. So this area here that is now not particles should be roughly equal to the area that's now spread out over here. Now obviously it's very hard to do in a sketch graph, but try and keep it roughly the same. So you can see the difference here that we've made. Originally these many particles were over the activation energy. Now we've increased the temperature, we've gone down to the right, and we have far more particles over the activation energy available for the reaction when they collide. So if the temperature goes up, down to the right, the temperature goes down from the original curve, you're going to go higher peak, so up and to the left, because the energy is going to be lower overall. So you would have a steeper curve, a much steeper curve that's higher, and then it would come down. And similar to before, this extra area here should be equal to the area we've lost over here. And we should be able to see, again, over our activation energy, less particles available to react. So you need to be very careful with these curves for temperature, that you do move them to maintain the number of particles as the same. The area under all three curves should be equal because the number of particles has not changed. You do not change the number of particles with the temperature. So last one, catalysts. Now catalysts, back to our topic 5 reminder, are known to reduce the activation energy required in a reaction by offering an alternative pathway. So if we were to draw this on our topic 5 graph, our reactants would not need as big an activation energy to be able to come out products. So we would reduce our activation energy and would call it EA catalyst, because we're taking a completely different route. We're technically doing a different reaction, just with the same end product. So you're taking a different pathway to get there. So the way we would show this on our Maxwell-Boltzmann should be reasonably easy to illustrate. If this is our original activation energy, and these are our original particles. We're not changing anything about our particles. We're not changing the temperature, we're not changing any of those things. What we're changing is the activation energy required to react. So you would draw your new activation energy, your catalyst activation energy, further to the left on the energy graph. So you can see that automatically means there are more particles available for the reaction. So all of these are now available to do the catalyst pathway, and all of these can do the catalyst pathway or the original pathway, which is why catalysts are so effective. They don't remove the original pathway. These particles here could still go by the original pathway, but all of these particles can go by the catalyst pathway. So you've increased the number of particles that can react drastically. And obviously, because catalysts are engineered for individual reactions, if you can find an even better catalyst that requires an even lower activation energy for its pathway, you could bring more particles into the potential reaction zone. So that's Maxwell-Boltzmann graphs. Obviously, we will use them to illustrate some practicals and things we do in lesson 2. Have a good day.